All right, hello. So what we're going to go over today is some of the introduction to the Google Cloud Professional Machine Learning Engineer certification. If you've been along with me on this journey, you know that we're going to have some machine learning, AI, and we're going to go multi-cloud eventually. So we're going to start a little bit with what is this certification? Well, first things we'll find out is that, let's see, I want to make sure that I have the right screen shared. So give me a second. Yes, we do. Okay. All right. One thing we want to do is know what the exam entails. So we'll see what goes over it. One, you have to register for the exam. How much is it? All right. So it's a 2-hour exam, costs $200. It's about 50 to 60 multiple choice questions. You can take it online or on site. You should have, well, they say 3 years of experience, which is relatively good. But to pass the certification, you just need to know what's on the exam. To get real world experience, that's how you make it really matter. So you should look at the Google official resources, follow along with this on this lecture, and then we'll go through multiple series in this and then follow up with some question and answers so you can get samples of what would be on this type of test. So let's go over this a little bit and give you some introduction to this. All right, let me save that. All right, so first things first, let's go here. All right, so the foundation of intelligent systems. Machine learning represents a fundamental shift in how we approach computing problems. Rather than explicitly programming rules and logic to solve every scenario, we provide systems with examples and let them discover the underlying patterns themselves. This paradigm shift enables computers to handle tasks that would be impossible to code directly, like recognizing faces in photographs, understanding spoken language, or predicting customer behavior. So Google Cloud Platform has positioned itself as a leader in democratizing machine learning, offering tools that range from simple SQL-based modeling in BigQuery ML to sophisticated custom neural networks in Vertex AI. Understanding the foundational concepts we're about to explore isn't just academic, it directly informs which GCP services you'll choose, how you'll structure your data, and how you'll measure success in production environments. Okay, and you can see how you look at your products by Google Cloud. All right. Um, okay, so there's 3 paradigms of learning here. All right. The first one would be supervised learning. This is learning from labeled examples. So imagine teaching a child to identify animals by showing them the pictures and telling them this is a dog or this is a cat. Supervised learning follows this exact pattern. We provide the algorithm with the training examples where both the input features and the correct output labels are known. The model learns the relationship between inputs and outputs and applies this knowledge to make predictions on new, unseen data. First, there's classification problems. This involves predicting discrete categories. When a radiologist labels thousands of medical images as benign or malignant, they're creating training data for a supervised classification model. Once trained, this model can examine new medical images and predict which category they belong to. The model has learned visual patterns that distinguish cancerous from non-cancerous tissue, patterns that might be too subtle or complex for humans to articulate explicitly. Then you have regression problems. These will predict continual numerical values rather than categories. Consider housing price predictions. Given historical data showing square footage, number of bedrooms, location, and actual sales price, a regression model learns the mathematical relationship between these features and price. When presented with a new house's characteristics, the model produces an estimated selling price. This isn't perfect prediction, it's statistical estimation based on learned patterns. Then you have fraud detection. So this will demonstrate supervised learning's business value. So credit card companies label historical transactions as legitimate or fraudulent, okay? Creating training data. Models learn patterns distinguishing normal spending from suspicious activity, unusual purchase amounts, geographic inconsistencies, or atypical merchant categories. The challenge lies in balancing sensitivity, like catching fraud, with specificity, not blocking legitimate purchases and angering customers, right? So how do you do this in GCP? In Vertex AI, you create a supervised learning model by first uploading a data set with labeled examples to a Vertex AI data set. For a classification problem, you'd specify which columns contain your target values, like Vertex AI AutoML. This can automatically analyze your features, it can handle pre-processing, and it can train multiple model architectures to find the best performer. The platform provides built-in metrics like precision, recall, and F1 score to evaluate model quality before deployment. So you can go into the console and do this. Let me see if I can get this loaded up. Okay, so we're in my account. So what she's going to do is click on the little hamburger menu over here. We're going to look for Vertex AI. We're going to go for data sets. API. Ah, it's not enabled. Jeez Louise. All right, so this will take a minute or two. That's fine. Oh, there we go. Close. All right, so we're in data sets. So we're going to look for create. All right. So in this create data sets, we can upload a CSV with labeled data. All right. And well, we can do an image, we can do tabs, we can do for text, we can do video. Wow, there's a lot. That's impressive. All right, so let's name this, let's say, information dump. All right. Let's do tabular regression. Let's see, forecasting. Let's create. And there's advanced options for encryption, for Google managed, or cloud KMS key, right? Which was owned by Google, which one's owned by the customer themselves. That would be us. All right. So from here, you can train your model. You can choose AutoML or custom training. You can define your targets and configure your training parameters like whatever you'd want, budget, or any optimizations, right? And then launch it. And Vertex AI will handle the infrastructure provisioning, distributed training, and hyperparameter optimization automatically. Okay. So let's go while this is going in. Okay. So the next one. Yeah. So you can see from here, how would you choose your own adventure and what is your use case for what you're using AI for? All right. Next one will be unsupervised learning. So this is discovering hidden structures. So unsupervised learning operates without labeled data. The algorithm must discover structure and patterns independently. Think of it as an exploratory data analysis elevated to algorithmic sophistication. The model receives input data but no correct answers, instead identifying natural groupings, patterns, or compressed representations. One is clustering. This groups similar instances together based on feature similarity. A marketing team might have customer data, purchase history, demographics, browsing behavior, but without predetermined segments. So k-means clustering analyzes this data and organizes customers into distinct groups. One cluster might represent high income, low spending customers. Another might show moderate income, high spending behavior. These discovered segments enable targeted marketing campaigns without requiring manual categorization of millions of customers. Then you have anomaly detection, right? So this identifies unusual patterns that deviate from normal behavior, right? In time series data, server metrics, manufacturing sensor readings, or network traffic, the algorithm learns what normal looks like. When values suddenly spike or drop unexpectedly, the system flags these anomalies for investigation. This approach works because anomalies are rare by definition. Having labeled examples of every possible failure model is impractical. All right, so then you have PCA. So this is principal component analysis. This addresses the curse of dimensionality. When entities are described by hundreds or thousands of features, data becomes sparse and patterns harder to detect. So PCA identifies the most important combinations of features, the principal components like that capture the most of the variation in the data. This compression enables visualization, so you can project high dimensional data in 2D or 3D. And this accelerates computation and improves the model's performance by eliminating noise. Okay, let's go back and see. All right, so here you would be able to set this up and upload a CSV, like we were saying. You select it and go forward from there. All right. All right, we're not going to go forward. We'll delete that. Okay, so where do I not see the delete? Oh, there it is, delete. Okay, so how would you do this in GCP? So BigQuery supports unsupervised learning with the k-means clustering directly in SQL. So you write a SQL query and you can train the cluster model and then you can predict cluster assignments, right? So you need a lot more SQL information. Let's get some of my favorite information. That's Vertex AI. All right. And K-means, right? This algorithm that groups your data into clusters to form unsupervised machine learning. All right. So you want to hold that. Okay. All right. Let's get this out. And this. Thought I saved that. Okay. So final piece, reinforcement learning. This is learning through interaction. So reinforcement learning represents a fundamentally different paradigm where an agent learns by interacting with the environment rather than from static data sets. The agent takes actions, receives feedback in the form of rewards or penalties, and adjusts its behavior to maximize cumulative reward over time. So what are the core mechanisms? Okay, an agent operates within an environment. It continuously makes decisions based on the current state. After each after each action, the environment transitions to a new state and provides a reward signal indicating action quality. So positive rewards reinforce beneficial behaviors, while negative rewards, like penalties, discourage detrimental ones. Through repeated interaction cycles, the agent's policy, its strategy for selecting actions, evolves toward maximizing long-term reward. So, exploration versus exploitation. Agents face a fundamental trade-off. Exploitation means taking currently known best actions to earn reliable rewards. Exploration means trying untested actions that might yield better outcomes. Pure exploitation risks missing superior strategies. Pure exploration sacrifices near-term performance. Effective reinforcement learning balances both, gradually reducing exploration as confidence in optimal policies grows. Then you have application domains. So game playing provides ideal reinforcement learning environments with clear rules, defined win-loss conditions, and fast feedback. AlphaGo is a mastery of Go through self-play that demonstrates this approach power. Robotics represents more complex applications, so teaching robots to navigate unpredictable environments, manipulate objects, or perform assembly tasks. Autonomous systems like self-driving, well, vehicles here will learn about optimal driving policies through simulated and real-world experiences. So, for the GCP exam, the source material will explicitly note that reinforcement learning isn't a major topic for the Google Cloud ML engineer exam. While conceptually it's important for comprehensive ML knowledge and understanding, however, reinforcement learning sees less emphasis in cloud data engineering context compared to supervised and unsupervised approaches. The exam will focus more heavily on unsupervised and supervised learning at scale. So this is our first recording. Before we get out of here, hit the like button, subscribe, share this with anyone you know taking the Google ML Engineering Associate exam. Thank you and have a good day.